You are standing at the front of a crowded lecture hall. The pacing is perfect. The logic is seamless. You are delivering a masterclass, drawing on 20 years of research. And looking out into the audience, you see students nodding along. It feels like a triumph. Then, a month later, you sit down to grade their final exams. As you read the responses, that sense of triumph evaporates. The answers reveal complete systemic misunderstandings of the core material. It is as if they were listening to an entirely different presentation. The immediate reflex in academia is to blame the audience. We write it off as shrinking attention spans, a lack of discipline, or the inevitable result of a generation raised on short-form video. The failure lies in the architecture of the classroom. Passive lecture transmission is neurobiologically incompatible with how human cognitive systems process and store information. We are trying to run modern software on incompatible hardware.
To understand why a clear explanation does not equal retention, we have to look at the biological default of memory. In 1885, German psychologist Hermann Ebbinghaus spent thousands of hours memorizing nonsense syllables to measure exactly how the brain treats information it does not actively use. This chart shows the resulting Ebbinghaus forgetting curve. It plots memory retention against time, and it reveals a mathematical reality of exponential decay that is absolutely ruthless to the standard lecture format. Within exactly 20 minutes of your brilliant conclusion, the average student loses 40% of the new information. Past the 1-hour mark, and half of everything you carefully explained is gone. By the time 30 days pass, which is roughly the gap between learning a concept and being tested on it, retention of unapplied information bottoms out at a mere 10%. The human brain is an active editor. Its biological baseline is to actively dismantle and dissolve neural connections that fail to prove their practical utility. Expecting a student to remember a single hour of talking a month later without active intervention is fighting the laws of physics. Active forgetting is the system working exactly as designed. Long-term storage decay is only the second half of the problem. The first failure point happens in real time, right inside the classroom, driven by the physical limitations of cognitive processing. Cognitive load theory distinguishes between two systems. We possess long-term memory, which has a functionally infinite capacity, and working memory, which is the incredibly narrow bottleneck through which all new information must pass. For decades, psychology operated on George Miller's assumption that this bottleneck could hold roughly 7 new concepts at once. Modern, rigorous studies led by Nelson Cowan have corrected this. Human working memory is strictly limited to exactly 4 discrete items. Researchers at the Massachusetts Institute of Technology recently discovered that this 4-item limit is tied to strict anatomical constraints. By studying macaques, whose visual working memory architecture mirrors our own, they found the limit is strictly lateralized. Because left visual fields are processed by the right hemisphere and vice versa, capacity is physically divided, 2 items per side. Apply this to a standard slide. Placing a complex chart, diagram, and dense text on one side physically overflows that hemisphere's capacity. A densely packed, highly detailed slide does not transform more education. It physically triggers a system failure in the student's cognitive processing pipeline, halting learning entirely. If these physical limitations are so severe, why do highly educated experts consistently ignore them when designing their courses? The answer lies in a cognitive bias known as the curse of knowledge, famously demonstrated in a 1990 study by Elizabeth Newton at Stanford University. Newton separated participants into 2 groups, tappers and listeners. The tappers were asked to knock the rhythm of famous songs on a table, while the listeners tried to guess the melody. Before beginning, the tappers were asked to predict their success rate. The tappers assumed the listeners would guess the song correctly 50% of the time. The actual success rate was 2.5%. This disconnect happens because an expert physically cannot regress to a novice state. When the tapper knocks on the table, they hear the full symphony of the song in their head. The listener only hears a disconnected, meaningless series of thuds. When an academic speaks, they are relying on 20 years of internal context that the student simply does not have. The audience suffers from a reciprocal bug called the illusion of explanatory depth. Novices consistently believe they understand the mechanics of complex systems just because they interact with them regularly. Designer Gianluca Gimini tested this by asking confident adults to draw a standard bicycle from memory. The results were spectacular mechanical failures, featuring chains connected to front wheels and frames that physically could not steer. A smooth, articulate lecture feeds both of these errors. The professor believes they have transferred their symphony, and the student believes they understand how the bicycle works. The illusion remains entirely intact until the final exam shatters it. Expertise relies on a specialized neurobiological method of perceiving reality that goes beyond a simple accumulation of facts. Look at the eye-tracking data of a novice analyzing a chessboard. Their chaotic gaze dart rapidly, overwhelming their working memory. Now look at the grandmaster. Their centralized fixations rest in empty spaces between pieces, recognizing massive, automated macro patterns, a cognitive process called chunking. Functional MRI scans actually confirm this shift. Novices burn out their prefrontal cortex struggling to process raw data. Experts have automated these complex evaluations down into their cerebellar pathways, requiring almost zero conscious effort to see the right move. This biological reality exposes the absurdity of the popular learning styles myth. Adapting your syllabus to cater to supposed so-called visual learners, or auditory learners, or kinesthetic learners is a complete waste of time. The brain learns through semantic meaning, not sensory preference. You cannot successfully teach an expert-level concept by simply showing it to a novice. Their brain literally lacks the fully developed neural architecture required to perceive exactly what you are showing them. If working memory is so constrained, and expertise relies on automated pattern recognition, the question becomes, how do we synthetically construct expert architecture inside a novice's brain? The most precise engineering solution comes from psychologist P.Y. Chen. Galperin and his theory of planned stage-by-stage formation of mental actions. Specifically, he designed what he called a Type 3 orienting basis of action. Galperin argued that we must stop teaching brittle, highly specific algorithms meant to solve existing problems. Instead, we have to teach the underlying invariant properties of a discipline. An invariant is the unchangeable core truth or structural logic of an object, a principle that remains absolute regardless of how chaotic the surrounding system becomes. Einstein isolated the speed of light as a universal invariant to build the theory of relativity. In law, the structure of a crime, the subject, object, and intent, is an invariant framework. It perfectly analyzes a 19th century horsebath, and it will perfectly analyze a cyber attack on a cryptocurrency exchange a decade from now. By teaching invariants, you equip the student with the expert's structural X-ray vision. You give them the capacity to independently construct their own algorithms for entirely novel problems. Galperin operationalized this into a 6-stage pipeline. It begins with intentionally placing the student in a situation where they lack the tools to succeed, creating the cognitive dissonance necessary to forge genuine motivation. In Stage 2, you completely offload the student's highly restricted working memory. You provide the invariant framework on a physical external matrix or map. Through Stages 3, 4, and 5, the student solves problems by physically tracing that map with their finger. Then, they vocalize the logical steps aloud to appear. Finally, under severe time pressure, that vocalization condenses into a rapid internalized whisper. By Stage 6, the action is entirely hidden. The student has internalized the external matrix into an expert intuition. But building this neural architecture is only the first step. We still have to prevent Ebbinghaus's stony day forgetting curve from dismantling it before the final exam. This chart illustrates Henry Roediger and Jeffrey Karpicke's data on the testing effect. It debunks the popular student strategy of repeatedly rereading notes. Students who read a text 4 times retained only 40% of the material a week later. But students who read it once and were aggressively tested on it 3 times retained a dominant 61%.